non-Newtonian hydrodynamics. And so it's a pleasure to have Huan Lei from Michigan State University, who's going to tell us about a very interesting machine learning-based model for looking at non-Newtonian hydrodynamics.
So because today is the Monday,
okay.
The introduction.
Okay, good. So today is the Monday, so maybe so we're not that many of us left, but a number of us are left. We should introduce ourselves to those who have started this week. Okay. Just say your name and where you're from and what you do.
Okay. Hello, my name is Ivar. I'm doing my PhD in Germany. I'm from Norway. I'm working on theory of liquid-liquid phase separation.
All right. Is this on? It's all right.
Yeah, okay. Yeah, I'm Luke. I'm doing my PhD with Tanny in Bristol and working on active pneumatics.
Hello, I'm Nikhil Desai. I'm a postdoc at DAMP working with Professor Eric Laga, and my research field is broadly on biological microhydrodynamics.
Hi, I'm Vivek Shenoy from the University of Pennsylvania. So my general research is in the field of mechanobiology, both theory and experiment.
Brad McIntosh, Rice University, soft and biosystems theory.
No, it's for new people to know where. Oh, okay. Let's say you're around.
Yes, so I'm Ryo Hanai from Kyoto University. I'm working probably on like active non-equal many-body physics, both in soft condensed matter and hard condensed matter physics.
Hi, I'm Tim Slukin. I'm from the University of Southampton. I do liquid crystals and statistical mechanical models and history of science.
Hello, I'm Buddha Chakrabarty. I'm from the University of Sheffield, and I work on soft and active matter and biological physics. So,
Hi, I'm Mike Cates. I'm based here in DAMT, and I work on active matter and statistical physics.
Hello, Mykola Tassinkevich, Nottingham Trent University. I'm working on liquid crystal colloid, microswimmers, active matter, soft matter in general.
I'm José Alnuchik. I'm from the Center of Theoretical Biological Physics at Rice University. I work for Brad McIntosh, and I do biological physics, anything from protein folding, chromatin, cancer, molecular motors. That's the area. Thank you.
Hello, my name is Andrea Jimenez Dalmaroni. I am from Cardiff University. I work in cellular systems at the scale of the cell, making theoretical models, and also in physics education research.
I'm Isaac Chenchia from Bristol. I work on solid mechanics, structural mechanics, and math biology.
Hi, I'm Tanny Liverpool, University of Bristol. I work on soft and active matter. And the floor is yours.
Okay. Thank you very much. Especially, I want to thank the organizer for inviting me to join this wonderful seminars. And it's really, I would say, it's really eyes open because my background is a little bit on the applied math or computation mathematics. I have been interested in the soft matter physics and the condensed matter physics for a long time. It's really eyes open. I see many very interesting research ongoing, and I will stay here for another 5 days. So I really look forward to further discussions. And for today's, as you can see, I'm going to talk about non-Newtonian hydrodynamics in the Newton Institute. Okay, so okay, so let's see if it works. Okay, so here's a bit of an overview of my research. So I'm mainly interested in developing reliable computational models for multi-scale systems. Okay, so I'm interested in starting from the microscale molecular level descriptions and develop coarse grain dynamics and continue hydrodynamics. Okay, so one of the recent research interests is focused on constructing data-driven models derived from this microscale description. And in particular, I would like to ensure the constructed models will return a clear physical interpretation and also respect the physical constraint and conservation laws, and also from a numerical perspective, be stable and efficient. And this kind of thought and effort is partially motivated by this kind of current debate or controversial opinions about data-driven or machine learning kind of approach. Oops, I'm sorry. This is kind of like we know that the machine learning-based models has become more and more popular nowadays in the kind of physical modeling, scientific computing, right? But on the other hand, it also acquires the reputation as a set of kind of like a black box trick without a fundamental principle, right? So there's kind of debate on this. So that's why I would like to ensure that the model I constructed will return this the clear physical interpretation and respect all the constraint and conservation law. That's something I keep in mind. Okay, and before we go to today's topic about the non-Newtonian hydrodynamics, I want to spend one more slide about why we're interested in multi-scale modeling. So here, just to quote a famous paper from Philip Anderson, last century. He has a paper. The title is "More is Different." So in this paper, he combined many opinions, but I think one of the main points made in this paper is that even if we have a very clear understanding of a physical system on a very micro scale level, or on a fundamental first principle level, right, it is still kind of very challenging to predict the collective behaviors of multi-scale system, right? And because of why? Because of this, the propagation of the broken symmetry and the propagation of non-linearity. So even if we know on the atomistic level what is the interaction, it can be still very challenging to see on the collective level what is the hydrodynamics, what is the diffusion, what is the transport, this kind of property, right? And that is why we focus on the multi-scale problems. Okay. Okay, so let us go back to the non-Newtonian fluid. So non-Newtonian fluid could be very complex, but on the micro scale levels, in general, it can consist of two types of molecule, right? So this the orange molecule is kind of like the small molecule, like waters. Okay. Well, besides that, we also have the macro molecule, like polymers. So on the continuum levels, the hydrodynamic models takes this kind of description. Okay, so here U is the flow field. Okay, P is the pressure, and tau, this tau S and tau P represent the stress arising from the micro scale interaction. And this, in particular, this part of the tau is where the computation challenge comes from. Okay, and in particular, for the small molecules like the waters, because the vibration typical relaxation times is much smaller than the hydrodynamic time scales. So for these kind of molecules, the stress can be well approximated by this Newton's formulation, right? Basically, it is proportional to the gradient of the velocity. Okay, but that may not be true for the big molecule like polymers. For this type of molecules, the relaxation time could be very long, could be comparable with the hydrodynamic time scales, or sometimes it could be even longer. So for these kind of molecules, we do not have a well-closed closures to represent the polymer stress, okay, tau P. Okay, so that is where the modern challenge comes from. Essentially, we do not have a self-determined or closures for this tau P. Okay, so before it goes to details, I want to use some simple system to illustrate the challenge. Okay, so let us start with something. Okay, like this. So let us take a look at this. This is just actually a very simple one-dimensional chain. Actually, that is my first PhD project. Okay, so you can see that this is just a one-dimensional chain connected by elastic bond, right? So nothing really special. And if we just write out the equation of motion for this this bead, the blue beads, it's just a linear system, right? Very simple. Okay, but then what about if we have a same system, let us define a big molecule, green particles. And this green particles is nothing but just the center of mass of a group of blue particles, okay? So it means that the system is unchanged. We just define a set of new collective variable, okay, at the center of mass of the blue particle. So what happened? So can we write out the equation of motion for these green particles? Well, we can try, right? Actually, this is my PhD, first PhD project. Okay, I start with something like this. It's okay, just like the elastic system. But is that sufficient? Well, the answer is no. It's actually, if we just take some ODE exercise, right, we can find out that actually we have some extra terms come from. Okay, this one essentially represents a non-Markovian memory effect, and the last term represents some kind of like a fluctuation arising from the different initial condition. Okay, and why we have these terms? It's just because this memory effect is arise essentially from the intermolecule motions, right? That we have eliminated when we do this kind of cross-graining. Okay, from these blue ones to the green one, to the cross-graining, we eliminate the degrees of freedom, then we get this memory effect. Okay, that's essentially a kind of like intuitive explanation why for the non-Newtonian fluid we have the polymers, and we have the constitutive laws becomes kind of like a non-Markovian, has a memory effect. Okay, so okay. So another perspective to understand the challenge for these transport equations, okay, is like this. Okay, let's see, because we have suppose we have a space, right? We have a collection of particles. Okay, each particle has some velocity, right, on the micro scale level. Okay, so then we want to do some kind of like a mapping from the micro scale to macro scale. So what do we do? We're gonna just define a grid space, okay? And for each grid, we're gonna define the macro velocities as the average of the particles within this grid, okay? So if we do something like this, okay, average, and then we take the Fourier transform of this U, okay, the continuum level velocities, okay. If we do the Fourier transform, we'll get this U hat. Okay, this U hat essentially can be written like this, and this P is just the momentum of the individual particle, okay? And then we take the time derivative of this Fourier modes, okay, like this, and we suppose that we're mainly focused on the low wave number. So which means the K is much smaller, okay? Much smaller than the resolution. And then given this, we can see that the evolution is proportional to this one. This tau is nothing but just the stress in terms of the individual particles, okay? But so far, this is still kind of a micro scale level description, right? So it's just depends on the stress in terms of the particles. Okay, so now let us do this kind of mapping. And in particular, we use this the linear response approximation, which assumes that the evolution of this Fourier modes is proportional to itself, and with a coefficient determined by the time correlation of this one, right? This is stress. And this, if we just take some statistical mechanics, and this part is nothing but just the definition of stress, right? So you can see that this one on the continuum levels, okay, it's basically proportional to itself with respect to this viscosities. Okay, then if we turn back from the Fourier space, okay, to the spatial temporal space, we get just the standard Stokes equations, okay, right? Okay, so far so good. But now, what the challenge is that, what about if we have this kind of big molecules? Okay, if we have big molecule.
For the memory out of the system, what happens? The integral there?
You mean this part, linear response part?
Equation.
There's no more memory because we assume that the linear response is valid here. Yeah. But exactly as you said, if we have this kind of macromolecules, then this approximation may not be valid, and then that's why we have kind of like a memories. Yeah, and just make an analog. Right.
Non-linear connection.
so linear response can have memory, but here we assume it is oh, okay.
I don't know why you're appealing to linear response as a reason not to have a memory.
Oh, okay. I got you. You're correct. I want to be, yes, I should be more accurate here. It is linear response in the, we use this concept to define this this shear viscosity, but you're right. We're here, we'll further assume it is non-Markovian.
That's the normal form.
It's kind of like a perturbation, right? Well, perturbation will have the relaxation back to the equilibrium is proportional to itself, and then the coefficient is determined by the
Stokes equation or Navier-Stokes equation is to do with an assumption about fast relaxation.
Okay, yeah.
To do with anything to do with linearity.
Time scale.
Okay. Okay. Okay, thank you. Yeah, but then if there's no kind of such a scale separation, so then this kind of a derivation is not valid. Okay, so, and that's why if we go back to this non-Newtonian fluids, okay, then we do not have a clear closures for this topic. Okay, so, okay, so to close the systems, so existing approach is generally based on kind of like empirical closures. So in general, we define some kind of field variables like C here essentially represent the orientation tensors of the represent the polymer configurations. With this C, we further assume that this polymer stress is kind of can be written as a function in terms of this C. Okay, and meanwhile, we further assume that the evolution of this C is governed by this HC, which is also empirical functions. But here on the left-hand side, this dc dt is the so-called objective tensor derivative, which needs to satisfy the frame difference constraint. Okay. So the physical interpretation is like this. So suppose we have the same physical system, but we observe it in two frames. One is inertia and the other one is rotating with respect to the first one. Then we should suppose we should get the same physical law. Okay, so that is essentially the impose a mathematical constraint to this dc dt. Okay, and besides that, we have some other closure like the integral closure. Then it directly relies on the empirical choice of the memory kernels. And a third one is kind of like the micro-macro couplings. Okay, so for these ones, the challenge is that we need to maintain a very computationally expensive micro-scale simulations to solve the micro models. So that is the challenge.
What about gradients in C? Are you going to consider gradients in C here, or can you zoom in? Or is it C varying in phase?
Yes, 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 yeah.
So H of C depends on gradients of C as well as C.
Yes, yeah. This is the general. Yeah, that is. Yeah. Okay, so sorry about that. So we have this is just a lot of papers on this field, but yeah, you probably cannot list all of them. Okay, so okay, but although all this kind of empirical model has been broadly used, but we have to see that we have to admit that there's certain kind of limitations. Okay, and the first the limitation is that this kind of models generally lack of molecular level fidelities. Okay, so generally this kind of G and H really depends on some approximation, like the linear approximation or mean field approximations. Okay, so it's really it's a challenge to really to deal with the kind of like a real system which has nonlinear interactions. And the second limitation is that we have kind of like we generally have a multiple choice of this dc dt, right? Usually we have the upper convective, lower convective, co-rotational. From a mathematical perspective, there's kind of infinite number of choice that can satisfy the frame difference constraint. Okay, and so in practice, we need to be very careful to choose this dc dt, right? So for many cases, we use the upper convective, but I see that this recent work from Tanis has very nice work about to consider the plane molecules, right? For that case, you see that we need to choose the lower convective. But if in more general sense, for more complicated system, is how to choose this DCDT. I think is very challenging in general. And the third one is about the more like the generalization ability, right? So in practice, okay, we often assume that the models admit some very simple structure like the dumbbells. But from an engineering perspective, the molecule can take a very complicated structure like the chain, the star, the loop, and it's very challenging to encode the heterogeneous into molecule interactions. So that is the thing we want to see if we can partially address this kind of challenge. And this really motivates us, our work about how to, if we can construct a machine learning based models beyond these empirical closures. So in particular, we want to learn the macro scale constitutive models directly from the micro scale descriptions. But in order to do that, there's still a kind of thing challenge we should keep in mind. The first challenge is that how to collect the training sample, right? So we should keep in mind that on the micro scales, the polymer configuration space has a very high dimensionalities, right? So it's very difficult to sample the configuration space. And even more severe challenge is that how to deal with this time series sample, right? So think about it. So nowadays we'll do this kind of like a machine learning models. If we want to learn something like a dx dt equals to fx, for many cases, so just collect the time series samples in terms of x, right? And then we'll take the time derivatives and we'll try to, then we'll try to fit this dx dt equals to fx in terms of time derivative samples. Okay, for many idealized case, we can do that. But in general, especially for this non-Newtonian system, that could be very challenging. Because if we want to collect the samples from MD simulations, the samples could superimpose with large statistical errors, right? And then if we take the time derivatives, we may get this huge noise. Okay, so it's just kind of not practical to really learn the constitutive dynamics from the time series samples. And even more severe constraint is about this DCDT, right? As I mentioned in earlier slides, from a mathematical perspective, there's an infinite number of choice that would satisfy this from a different constraint. But in practice, how to choose this DCDT, okay, that is a challenge. It's just like called the Seagal's law, right? A man with one watch knows the exact time, but a man with two watches don't know the exact time. So we have an infinite number of choice. So it's really don't know how to pick the right one. So that is something we should keep in mind. Yeah, sure. Yeah.
C is the second rank tensor, or not yet.
So here we're in our models, we're gonna stay with the second rank tensor, but in practice, we may get even higher order tensors.
Okay. As far as I know, if you have a second rank tensor, there are indeed an infinite number of choices, but they're spanned by a single parameter. Right?
Sorry.
The choice you have in dc by dt is governed by a single parameter, the slit parameter.
Single parameter?
Yes. Convected, low convected, co-rotational. They all live in a single family with one parameter that takes you continuously all the way through. That depends on the collective variable we choose for definition for C, as we're going to show. Yeah. Okay. No, that's true.
For my case, I find a more generalized forms which has some extra terms. It's not in this single parameters family. I will show it if you slide. Okay. Sure.
When you see symmetric.
C is symmetric.
Symmetric.
Yes. Yeah.
But it's always symmetric in any exchange of things.
Okay. Yeah. Okay. So to deal with this, okay. So the first idea is that we're gonna seek explicit micro-macro correspondence. So which means that, okay, we're gonna start from the micro scale descriptions, okay, kind of collection for molecular configurations. We're gonna learn a set of encoders, okay, this B, okay, and then we'll take the average, which will get a set of generalized conformation tensor C, Okay, and then we're going to utilize this C to construct the polymer stress tau P and the constitutive closures like H and the dCdt here. Okay, so here I want to emphasize that this C are not the standard moment to approximate the polymer configuration densities. Okay, in fact, here we totally give up the direct approximation of this PDF here, because from a numerical perspective, if R has a high dimension, right, nonlinearity, it's very challenging to directly approximate a PDF, right, in terms of R. So if it is 3 or 10 or even larger, right? So here, C which is directly learned to seek the best approximation of G and H. Okay, so it will be joint learned. Okay, so in fact, we totally give up the direct approximation of F, and I believe that is the reason why here we can deal with these high dimensional problems. Okay, without worrying about this F. Okay, so and of course we need to carefully choosing the formulation of this G and the encoders and the H and the dCdTs. Okay. So, okay. So let's start with the encoders. Here, we're gonna start with the dumbbell molecules. So first, let's assume that B is a vector. So if B is a vector, then it should retain the Fermi different constraint, which means that if the molecule on a micro scale, if a molecule has a rotation, right, this U is unitary, then the output B is also unitary. Okay, so given that, then we can show that this B must take these forms. Okay, and here little g is a scalar function. Okay, but if that is true, then if we take down some average, we just get a trivial result. Okay, because why? Because 1, 2, and 2 are essentially the same, right? So it's trivial. So in order to get a non-trivial forms, so the next choice is the second order tensors. So here, if B is the second order tensors, then if we have a rotation on the micro scale, so then you must satisfy these relations. And a simple non-trivial choice is like this. And here, B is like F and F transpose. Okay, and F is essentially a vectors. Okay, and if F is a vectors, then we can use this result, right? So F take these forms. So that is the generalized forms for these encoders. Okay, for the dumbbell molecules. Okay, so here G is the encoder function that we're gonna learn. Okay, so then we can further generalize these forms for the multi-bit systems. So the idea is all similar. So we're gonna define a set of rotation symmetry configuration R, okay, with rotating with respect to the micro configuration, and a set of rotation invariant configuration R star. And then we can use the R and R star to construct these encoders for the generalized molecules. Okay, so I was gonna see all the microscale connectivity and configurations can automatically be encoded into this. Okay, so now we have the symmetry preserving encoder formulations. Okay, for this B and essentially C. So the next task is how to construct the dCdt and also the G and H such that this also strictly preserve this symmetry constraint, right? So that is the next task. But at the current stage, let's hold on this question for a moment, but ask the next question, the other question. So suppose we have this sort of generalized form, how we can construct the proper formulations without using the time series samples. Okay, so because currently we have this kind of encoder, right? We need to learn this constitutive closure. It seems that we have to deal with some dynamic problems, that how to avoid this. So here comes to the second idea, is that it's actually an observation, is that since we have established a mapping from the micro to macro, right, from encoder to conformation tensors, then we can derive the dynamics of these C's, okay, directed from the connected, essentially Fock-Planck equation in terms of this F, okay. If we do that, basically we get this formulation, and we can see that this formulation essentially provide us, okay, exactly the dynamics of C, except that it is on the micro scale description, okay. And here we can see that, I'm gonna skip the details, but we can see that all the micro level the details, the interactions, like the connectivity, and also the interactions can be automatically encoded into this generalized Rouse matrix and the potential functions. Okay. And furthermore, we can assume, or we can see that the equation 2 will rigorously preserve the rotational Fermi different constraint. Okay, so I'm gonna skip the details, but just use an example of the dumbbell molecule to show, because on the right-hand side is quite straightforward, but we're gonna focus on the left-hand side. For the left-hand side, right, we have basically two terms. Again, we're gonna see and check the dynamics in two frames, and the other one is rotating with respect to the other one with this unitary matrix. And we can see that if we combine these two terms together, actually these two terms automatically satisfy this Fermi different constraint. Okay, so with this result, then we can see that actually the first two terms, essentially the two terms on the left-hand side, essentially provide us a forms of the generalized objective tensors with the microscale description. Okay, so which means that we don't need to really guess which one is the one objective tensor derivative we should choose, but we can directly construct it using these microscale definitions. So that is the main idea. Okay. Yeah, please. For the dumbbell, A is just a trivial result. It's just, I think it's kind of identity or something. Yeah. And V is just described by some kind of just a dumbbell, like molecule depending on the bond length.
A linear spring or non-linear spring for your dumbbell? Well, what do you want to use it for the?
For the dumbbell, I just use a non-linear spring. Yes, and yeah. And for the multi-bead, we introduce more complexity, like the different connectivity, the structures. Okay. Yeah, but here the proof is just based on the dumbbells, but yeah, but we can do it for the more generalized forms. Okay. Yeah.
So see how you prove that for dumbbell.
Yeah.
And you can probably move it for any non-interacting individual molecule.
Yes.
But in general, the form of the slip parameter or the total derivative does depend on interactions between molecules, which I don't see in that.
From for the object tensor derivative, it is defined like this, and this one is essentially only depends on the connectivities. It does not really depend on the V.
Sorry, is there one dumbbell or many?
This is just one dumbbell. Yeah.
Well, I'm saying, but there are many. One of the ways that they interact does change the total derivative.
You mean if we have many dumbbells?
Depends on interactions
between the dumbbells. Yes, that's correct. Here we only consider the intermolecular interaction. You're absolutely right. Yes.
So in the case like this, you can do the micro to macro and keep track of the derivative you need.
Yeah.
But I'm just saying that in general, you can't.
In general, when you say I want to confirm my understanding. Among the molecules, I have some slides about this. I'm gonna talk about this after I finish this. Okay. So here we just get generalized forms, okay, for the dumbbells and actually also for the multi-bead system. Okay, so if we put everything together, now we get kind of like a machine learning based models for the non-Newtonian fluids. Okay, so we can see that the model, the formulation is actually resembles the conventional models. The only difference is that certain modeling terms is represented by a neural network that strictly preserves the rotation symmetry. Other than that, it's essentially similar, right? And in order to construct the models, we can see that each term has a clear physical interpretation on the micro scales. Okay, so which means that we can directly approximate this function G and E and H, okay, on the micro scale levels without using the time series samples. Okay, and why? Again, this is because we explicitly utilize our knowledge, okay, of the physical the governing principles on the micro scales, okay, rather than use this kind of black box learning, right? So we directly pass the basically essentially the micro scale models to the macro scales. Okay, so that is the okay. So the next step, I think essentially the last step for these models is to design a set of symmetry preserving functions, okay, for the modeling terms, right? So we already have the symmetry preserving encoders for this B, right? We have seen this earlier. I think the remaining task is for the second order tensors G, H, okay, and for this one, we can use we can utilize the eigenspace for the conformation tensor, right? For example, we can pick one, the C1, which as the regular one, end-to-end tensors, the regular one, and then we utilize the eigenspace of C1 to track the rotation, such that the function remains a framing difference. Okay, so that is the basic ideas. And the last one is the fourth order tensors, right? So we see earlier we have generalized forms, okay, and then we can design some symmetry preserving formulations for this object tensor derivative. Okay, again, I'm gonna skip the details, but here it's just the E1 and E2 are basically second order tensors, right? So then this E is the fourth order tensor. And if we put everything together, then we can see that the final forms essentially will resemble the upper convective conformation convective tensor derivatives with an extra term. And these extra terms represent basically the nonlinear coupling of the field variables with the fluid, okay, on the micro scales. Okay. So that is the interpretation for the second terms, okay. And of course, we do not know this term explicit a priori when we do the modeling, but that's not a problem because we can learn this term directly from the micro scale description, okay.
How to learn this term from the micro description or the tensor? How much data do you need?
Oh, actually, I'm gonna talk about it. So.
Ever.
So actually the training is training is not I would say it's not that challenging for the case we studied here. Yeah. So as a summary, right, we have a single dumbbell with two larger, right? Okay, yeah. Okay. So we have basically we have a set of kind of modeling terms, right, in terms of G and H, right? So here we put everything together. And this one in the bracket basically are the training sample collected from the molecular dynamic simulations. Okay. So here I want to emphasize that also these encoders, although does not show up in the macro scale levels, but it still involves in the training. Okay. In the sense that, right, as we said, it's a joint training where basically simultaneously optimizing the encoders and their continuum level representation. So this is somewhat similar to like what we do for a function approximation. We're simultaneously optimizing the function space and the approximation coefficient. Philosophy is similar like this. Okay. So yeah, go ahead.
Training sets.
Yeah.
I mean, presumably, how long, how big it has to be, somehow must depend on the amount of things you want to learn.
Yeah.
So I mean, so basically, the more complicated these things that you have to learn, the bigger your training set has to be.
Yes.
Just you check how it scales. I mean, you can then see how as you make your functions more complicated, how big your training set needs to be before you start getting used to learning.
Right. So I can tell this in the next slides. So it's kind of so to answer your question. So actually, the collection of training sample, at least for the current problem, is not that challenging. Why? The fundamental reason is still because we only need discrete samples. We don't need time series samples, which means that we can establish a replica of MD simulation simultaneously with different let's say external field, like the different flow field. So we just need to kind of like take a lot of pictures, right, of this molecule configuration. So yeah, it's kind of it's embarrassing parallel. Yeah. So in practice, each box is needs on the order of 100 to 1,000 polymers, and the number of like this box is on the order of 100 to also on 100 or 1,000. Yeah. And then yeah, we take these kind of pictures, right? So we plug into the joint training in terms of the encoders and their macro scale representation. Okay. Okay, so here's some numerical examples. So here we consider start with the Fini is basically a nonlinear bond interaction, right? So as mentioned, so here we only consider the intramolecule interaction. We do not consider the molecule between them. Okay, so here, and then we're gonna compare with two popular empirical models, like the Hookean model, essentially based on the linear approximation, and the Fini-P is actually a mean field approximation. That is the two types we're gonna compare, and the model will be validated with different flows, and then we're going to use the same training set. So we want to check if the model has certain kind of generalization abilities. Okay. So the first thing we check is basically the conformation relaxation. So here we do not have flows. We just have a configuration collected from high temperatures and see how it relaxes to the lower temperatures. Okay. So here for these models, we use those 3 encoders. So the first one, as I mentioned earlier, is a trivial, right? It's just like the standard one. And then we have 2 other encoder functions. And here, the blue curves is basically the MD simulation result. And the red curve is the MD simulation result. And the blue curve is our models. And then we also have 2 other, like the Hookean one is the linear one, and the Fini-P is the mean field approximation. And you can see that the machine learning models agree well with the MD for these systems. Okay.
What 1 and 2? What's 1 and 2?
1 and 2 is basically we have different set of the empirical models to want to see. Sometimes we can tune this empirical model, right, to so that it has a good approximation with the MD, just on purpose to tune the parameter. But once let's say we have a good agreement with the tau with stress, then we see that it will have a large deviation for the C. So we cannot really have a good agreement simultaneously for the empirical models. But it's, on the other hand, right, if you have a good approximation for C, then it does not have a good approximation for tau. Yeah.
Why is it? The order.
Yeah, because this is because in general, I would say that's because the empirical model, this Fini-P model, cannot really capture the MD model in general. I think that's the fundamental reason. So if we just on purpose tune it to let it fit with some physical, right, variables, then it shows large discrepancy for the others. Yeah.
But if you tune some physical variables, then 1 and 2 cannot both satisfy the same physical variable, can they?
Yeah, so here, because the Fini-P has some model parameter, right? I just tuned one of the parameters, let's say for example, let the Fini-P model to have a perfect agreement with the MD result for the stress. But what if we do it like this, it will shows the large deviation for the others, like the conformation tensor. And then we can do the other way. We tune it such that it has good fit with the MD for the conformation tensor, but then it will show discrepancy for the stress.
Exactly, that's what I basically both of them seem to be better for both.
Oh,
is that mistake?
Oh, this is visualization here. 2 has a incorrect prediction on the equilibrium stress. Yeah, sorry, here, this one, 2. Yeah, okay, yeah, yeah.
What about 1? Is 1
one has a good approximation of the initial, right, the stress. It has good, right here.
It's at the top.
Yeah.
So you're only studying here the stress, the initial stress.
Yeah. We cannot ask much because in general this model is there. Yeah. Sorry, thank you for asking. Oh, sorry. It's just a 2 parameter set for this empirical model and FINIP model. Yeah. This one is the present model. Yeah. Okay. So next we'll move to the reverse positive flow. So we have the external force applied to the systems, and again we're gonna check the flow evolution of the flow. Okay. Here. The red is the MD and the blue is the machine learning, and the other 2 are the empirical models. Yeah, you can see that it has a apparent deviations for these empirical models. Okay. And next, I also want to discuss a bit about this generalized objective tensor, right, derivative, right? So we see earlier that for the current models, actually we have extra terms, additional source terms here, right, represent the nonlinear coupling in the micro scales. Okay.
That derivative is meant to be linear in C and linear in velocity and linear in the special derivative. And if it's nonlinear, it's on the other side of the equation.
I think then if that is the case, then I think it's really about the definition, right? So here I defined it like this as the evolution of the C. This is a nonlinear term that we have to include in the
put nonlinear terms in the equation somewhere. I'm just saying that directed derivative, C, is a linear operator acting on C. That's what a derivative is. It can't be nonlinear in C and called a generalized derivative. So if you have nonlinear terms, but they belong on the other side.
Okay. So then I got to your point. So you said that because this has nonlinear terms, then we cannot call it objective tensor derivative. Okay. I got it. Yeah. So this I got agree. So I call it this is because we derive it from derived it from a Fock-Planck equation from the left hand side. But I agree. Yeah. These terms, right? These 2 terms with together is where we derived this term, the term you see.
Yeah, so it's linear in velocity.
Okay. But
it's not something here that's not here. But we have to be neglecting something here, right? It's not exact.
It is exact. It is exact. So if we keep
that's fine, no problem.
Yeah, but this term, right. So here, right. So when we derive it from the microscale, and this term needs to be here when we derive it from the kinetical models, and that's why I put them together, I group them together. Okay. It's fine if you think if we follow your definition. If we call it this one, we still focus on this one as the upper convected. Then this go. Okay.
See, is there a linear part inside to separate that into something which is linear and something which is not linear? Because I'm used to the case where you do get the different linear derivative with this slip. And I'm not quite sure whether that would come out as part of your E term, or whether that thing is actually quadratic in C or something which couldn't give you any correction to that linear boundary.
So if we follow your definition, we can call this one, we'll call this one objective tensor derivative. If that is the case, but then my point is that we still need to keep this term, which is unknown a priori. Right, we need to keep these terms in the constitutive dynamics. Otherwise, we do not have the correct prediction. Okay.
Now, I guess one of the things that I could imagine that,
Yeah.
that if I have a complicated system, that maybe is there some way in which that term could decompose into something which is one of them is essentially it's hard for me to see how it could be independent of C. Either of the E terms. So it
looks like it's quadratic in C.
Exactly, because it's a leading order.
But unless E has some piece which is constant, in which case there would be a linear bit hidden in there.
Yeah, but I can't think of a way for it. I can't think of a way for it to be constant.
So this, yeah,
it seems to me that it has to start a quadratic order.
Right. So, but then this term appears because on the micro scales B is not necessary to be quadratic, because we have defined this kind of generalized conformation tensor, right? As B as this little g and R transpose.
But you think that find it, but then I don't know how you get it.
It's because of this one, right? So if you see here, B, if B is just R and R transpose, then we just then we proceed, right?
But
then we
don't say it's exact, and also can and that's what I'm really confused. But maybe what I'm not following. But
okay, so B if B is a standard encoder like a R and R transpose, right? So we'll put this one into this, and then we'll get a standard upper convective. But B here has the little g, right? That is g squared and R transpose. The little g is the encoder. The encoder function could be nonlinear. And then if we have this gradient here, it applies to the g, the encoder function, which is nonlinear. And then it will have some extra term. That is the source term that I present later. Like that is the extra term here, this little g. Because the nonlinearity of this little g. And I agree if we do not call this, if we keep these terms as the upper convective term, as the object tensor derivative, that's fine. But then here, this extra term needs to be in the constitutive models. Otherwise, we do not have the consistent prediction.
Maybe we should continue this.
Okay. Okay. So that's the that's the main point here. So we have some extra terms here. So if we do not have these terms, we have the large discrepancy. And then we have some numerical result for the multi-bit systems. Okay, so here we also compare the result with respect to the different molecule structures, and then with the MD simulations. Okay, so for all the cases, I have a good agreement. Also the hysteresis loop and the Ormsby flows, we have so good agreement with the MD simulations. Okay, I also have the 2D, okay, the Taylor vortex, and for the chain, the stars, also have the good agreement. And here's something actually Tani asked me the conference in Japan, asking what about if we have the intermolecule interaction. That this is some effort we're doing, but we haven't finished yet. So the idea is that we consider now the previous result will consider the interaction inside the molecules, but we also want to account some of the intermolecular interactions, right? So here we were doing some kind of like a cost screening first to get the reduce the models for this calculate the equation of motion for the cost screening molecules. Okay, so here's some result. We design some kind of symmetry preserving neural network for the many-body non-Markovian memories, and then our plan is that we're going to start here. Then we're going to design some new features to account for the intermolecule interactions, and then we encode it into the system. And that's just something we're doing ongoing work. Okay. Let's see some result. Because I think I'm gonna skip. Okay, as gonna summaries. I think so we have machine learning models. Okay, so I want to emphasize that we do not really utilize the time series samples that we do to construct the models. I think that's something very common nowadays in the machine learning community. Use the time series to fit the dynamics, but here
I think we use like the governing principles, so we just use discrete samples. And also I want to mention that we can avoid the direct approximation of the high dimensional PDF because it's numerical challenge. On the other hand, I think the models has some systematic be reliable and has the capability to systematic pass the microscale interactions to the macro scale, and has provided a generalized form of object tensors, but of course depend on the definition how you call it, and I think strictly preserved all the framing different symmetries. Okay, so I want to also mention about some of the ongoing things, especially I'm interested in the non-dilute and the dense polymer solutions, and also the application to software matter, the biological system, and I look forward the discussion with you. Thank you.
And for a very interesting and thought-provoking talk. And we've had a lot of discussion already during the talk. So are there any comments or questions? Okay.
On the first point here, the intermolecular interactions going away from the dilute.
Yeah.
Can you say a little bit more about the prospects there?
So here, thank you for asking. So here we try to, because we currently try to learn some kind of like the reduced model, right? Then this really inspired us to see if we learn kind of set of like features that represents the interactions between the molecule in terms of like this kind of feature. And then our plan is that to see if we can then further define some kind of field variable in terms of this intermolecule interaction features. And that's something we plan to incorporate into the current non-Newtonian fluid in the continuum level.
But like what classes of interaction would be able?
I think if you have very local interactions, should be no problem. But after that, things may become complicated, right? There's overlapping interactions or no local terms. I don't know if you thought about it.
So here, this is still kind of focused on the kind of the neighbor interaction. I agree with you. If we have a very complicated system, then we may need to think about something more global collective variables to characterize the interaction. Yeah, I agree.
So it's the shape of the molecule. It's for people online. Oh, I think they don't hear this.
I'm just wondering, is the shape of the molecule accounted at any point in this analysis? Then it might become more like liquid crystals, right? Things may be more elongated. So is that in the model already, or?
This is currently we do not we haven't considered the liquid crystal yet. The liquid crystal must design something that account for the anisotropic effect. So, but
the molecules could have a preferred shape, right?
Yeah,
I think you had some star shape. You had some
right. So
topology for molecules. Can you say something about
right.
those?
So this is something. This is something we can this is something we can capture. Yeah.
So
yeah. So that is automatically encoded into the kind of generalized Ross matrix. That's all this in terms of these connectivities, right? Yeah. It's automatically just directly encoded into the kinetic equation. Yeah.
Yeah. Maybe dilute or also when the fluctuations are small in some kind of some mean field level where you got. I think that was the place where. I've got a question more about the neural nets thing.
Okay.
So what's the structure of the deep neural net that you're using? I mean, does it matter? Do the results matter? What kind of what kind of nets you use?
So the neural network we use to our experience, it doesn't really matter. So currently we use really the dummy fully connected neural network. I think the more so we put a lot of thought is about how to preserve the symmetry constraint. Yeah, how to design these forms. But in terms of learning this kind of design formulation, we find that it's the fully connected is doing well.
So for training these neural nets, how much data do you need? It's a vague question, but I'm just trying
Yeah,
to
sure.
Is it training for like a day or like weeks or?
No, that it's kind of on the order of days. Yeah, days. Yeah.
So again, following up on that, I mean, so I think what you're saying is that essentially what you can do is you, instead of doing a simulation, you can just essentially generate some kind of, if you want, configurations which have some properties, and then you try to from that learn the parameters.
Yeah.
Now I could imagine that if I have let's say I have a suspension of some polymers, something like that, and then I do a very, very strong deformation, then I know that my polymer configurations are going to be very far from equilibrium.
Yeah.
So then so in order to capture any type, I will have to somehow sample that distribution accurately.
Yes.
So how would you do that here? Because it's how can you make sure that you generate the right set of things to learn from, basically?
So yes, that's a good question. So currently, so as we know in general, currently, I think all these kind of neural network representation can do, I think, good job for the interpolation, but it's not doing good for the extrapolation. So as you're absolutely right. So we have to ensure that the regimes that we study that has been covered in the training set. So with that, so I think there's two things I'm considering. One is about the kind of like enhanced samplings in terms of MD simulation. So we want to ensure that the systems can overcome kind of local energy barriers. So ensure that it can be well sampled in the phase space that we're interested in. And the second thing we're also thinking is about imposing some kind of adaptivity into the training. So it's kind of like, it's sort of like the active learning. It's kind of like we want to kind of like adaptively include the new training samples that kind of have the large approximation of training errors. That's something we're currently doing. Okay.
If there aren't any more questions, if not, let's thank Huan Lei for a very interesting talk.